last time we were talking about the smallest carbohydrate, which is glyceraldehyde. We're going to draw it up here and then build the model of it. And then we're going to look at how this thing called Fischer projections, which is how we often visualize these types of structures. So as we mentioned last time, at the top of the sugar structure, there's always an aldehyde. Not always, but there's often an aldehyde. Okay. Then we get another carbon that has an OH and an H. So let's do it this way. We'll put the OH on the wedge, and the dash and the H on the wedge. And then we have another carbon with an OH attached to it underneath. That bottom one doesn't, the dash wedge thing doesn't matter because the two hydrogens mean that there's no stereochemical restrictions there. All right, so I want each group to build this model. You can use whatever colors you want for stuff, but it is actually important that you separate the double bonded O from the other things. So you can either just use a different color for that, or if you have those curvy, these things, you can actually make a double bond to oxygen. Either way, you just want to make sure that you know which one is the aldehyde versus the other two carbons. And then so you've got 3 carbons connected together. You don't have to put all the hydrogens on there. So let's just build the carbons and the oxygens. So you got your 3 carbons. Make sure everything is in the exact same orientation as what you see up there. So if you're starting at the top, you should zigzag from kind of top left to bottom right to bottom left. Like that. So make sure it's that way and not this way. It's actually going to make a difference. So this way, not that way. You got your carbonyl on the top, which you can put on however you want to do that. I'm going to use blue because I don't have very many reds.
You want us to clean the hydrogens?
No, we'll leave the hydrogens off.
Do the oxygen?
Do the oxygens. So keep kind of putting your structure back up there, make sure that it looks right. And the key here, because we're so concerned with this stereochemistry, is to make sure that the oxygen is going the correct way. So when you have in that middle carbon. So when you have your basic structure like that, we have to make sure to put that oxygen pointing away from us, not towards us on that middle carbon. But yeah, so that's a good start. And then we got to make sure to get that oxygen away like this. So the zigzag is going this way, the aldehyde's on top, and the oxygen is pointing away. That's good. Okay.
And then how do you do the bottom one?
What?
The bottom one?
The bottom one is just going to be another carbon with another OH coming off of it. It doesn't matter. You can notice there's a bunch of open holes on that bottom one, so it doesn't actually matter which way you put that because it can swing around however it wants. So the middle one is the oxygen going back. We don't have that. Because it's on that dashed one. sense? Got it? Anybody else have trouble building it? Okay. So when you've got that, you might not have enough pieces to make it look exactly the same. But we're going to also look at the mirror image or an enantiomer of this, which is where everything's the same, except those middle two are switched. So in the middle ones, the OH is now coming out at you. So if you have enough pieces, try to make that one also. Remember, the rest of the structure, the colors, doesn't really matter. All you need to know, all you need to be able to do is tell the top from the bottom, so know which side has the aldehyde on it. And then that middle carbon is what we're really concerned with. That's what's important, to make sure it's going the right way.
So you said if we have to find out a way to tell it's an enantiomer, or it's called enantiomer,
Yeah.
then all we have to do is just see if the two oxygens are mixed, the OH and H.
For this structure, yeah. As we get to more complicated structures, the rules change a little bit. So, but yeah, the actual rule is all of the dash wedge ones have to be switched for them to be enantiomers. In this structure, there's only one spot that has them. So that's why that one is the only one that changes here. All right, so I am out of my colors, so I'm going to use the other blue here. All right, so when you're done, you should have that original one that showed the OH going out away from you. And then you should have the new one where everything's the same except the OH is now coming toward you. So one of them has the OH going away in the middle, and one of them has the OH going toward you. The difference in that middle one. This one's pointing away this way, this one's pointing out towards you. Nope. It's moving from like this direction. It's not rotating, it's in a different position. They're actually different because you can't interconvert them. They're not superposable, they're not the same. If you put them right up next to each other, to get something like this, so all of the, sorry about my different colors, but all the atoms line up perfectly, except in the middle. One of them's coming out this way, and one of them's coming back that way. So that makes them non-superposable. They're not the same. One of them's going that way, one of them's going that way. Ready to have that? All right. So that's one way to express the structure, but as we get into the more larger sugars that we're going to see in a minute, this becomes really difficult, kind of what Alina was alluding to earlier, that we have to look for all these dashes and wedges and see if they're all switched or see which one's in which position. It ends up getting kind of confusing. So there's a slightly different way that we represent the stereochemistry of sugars that makes it a little bit easier to see this. It's called a Fischer projection. And this is how it works. You take one of your structures and you look at it from the side, kind of from the middle, from the side. So if this is like an eyeball. Instead of looking at it from the front, the way we drew it here, we're kind of looking at it from here, going that way. And so in that form, we have what we call a Fischer projection. So take your models, whichever one. You can do the one that I just point the arrow for, which is the second one that we did, or you can do the first one. So you're going to take your model, okay, and you're going to look at it like this. So instead of the side where the zigzag's going like that, you're going to look at it kind of straight on so you can't see the zigzag anymore. So it looks like these carbons are all lined up. Does everybody see that? So you turn it so that you're looking straight on to that middle carbon, like that. And when you're looking straight onto it, that OH, instead of thinking about it being front or back, the OH is going to be off to the left. See it off to the left? Or if you use the other one, where'd the other one go? Here it is. Okay. So now the difference in the two is much more distinct because in one of them the OH is clearly going to the left, and the other one it's going to the right. See that? You're looking at it kind of straight on like that. One's going to the left, one's going to the right. So that makes it much more obvious, the difference between these, than looking at it on the side and saying, okay, one of them's kind of going back and one of them's kind of going front. This way we can say, okay, one's definitely left, one's definitely right. So that's what a Fischer projection does, is it allows you to look at it in, or to draw it in 2 dimensions that shows you the left versus right thing, the stereochemistry being really clear. So in a Fischer projection, rather than draw the individual C's for carbons, make that a little more even, we use the line structure convention that anytime lines cross, that's a carbon. And so our top has our aldehyde, which we can abbreviate as CHO. Our bottom is still CH2OH. And then depending on which one we're looking at, the OH is on one side and the H is on the other side. So for this one that I drew right here, the OH is on the left and the H is on the right. When the OH is on the left, we usually switch it to an HO just to make it clear that it's the oxygen that's connected and not the hydrogen. But you could write OH there also. I wouldn't have a problem with that. So this structure now is represented by that Fischer projection like that. And it makes it really clear that the OH is on the left. So if we want to do that with the other one, we can do the same thing. But because this one is the enantiomer, the OH is going to be on the right and the H is going to be on the left. And you should be able to see that in your model also. So pick it up, look at it, get it in the right position, and make sure that you can correlate those types of structures with what you just built, so that you know that's what this is. All right. Now, once we get it in this Fischer projection, these things are really used for carbohydrates and for amino acids. So we're going to see them in these chapters. They're not really used in other areas of chemistry quite as much, but they're really helpful for this. One of the reasons that they're so helpful is when we look at that, we can clearly just figure out which type of sugar, which enantiomer of sugar we're talking about, the D or the L, which are the 2 types of sugar. Question? And carbohydrates, yeah. Yeah. So like we're dealing with carbohydrates now, we'll get to amino acids in a couple chapters.
So for the finger to the right, to the left.
Well, kind of. So you're always twisting so that the middle of the chain is like coming out at you. So in other words, we looked from the right because this chain was zigzagging to the right. But if we had drawn it zigzagging to the left, then we'd look from the left. And you won't have to do this conversion like that. What's important for you to be able to know is what this projection means and where it comes from, but you don't actually have to be able to do that drawing. Okay. But what we get from this is that because this OH is on the right, this particular sugar is D-glyceraldehyde.
The OH is on the right.
When the OH, the bottom OH is on the right, because we're going to see some in a little bit that have multiple OHs. So the bottom one is on the right, it's the D-glyceraldehyde. If the bottom one is on the left, then that's L-glyceraldehyde. And all or almost all naturally occurring, not quite all, but almost all naturally occurring sugars are the Ds. So even though this seems like a really subtle difference, the difference between having the OH on the right or having the OH on the left means a totally different interaction with your body. All of the molecules in your body, I guess not all, but a lot of them, a lot of the important molecules in your body have this same kind of handedness, this like asymmetry that we call chirality. And so anything that interacts with your body, that chirality becomes also important. And that's why we're spending time looking at this, because the difference between these, even though they look very similar to a living thing, is huge. It's a huge difference. What? The right one is called D-glyceraldehyde, and the left is L-glyceraldehyde. Yes. So each sugar is going to have two forms, the D and the L. And they're mirror images. They're enantiomers. We should write that. So the D and the L are enantiomers, which if you remember from Tuesday means non-superimposable mirror images. So they're mirror images that are not exactly the same. Not be placed right on top of each other. All right, so let's look at some bigger sugars. So what happens is you can add more carbons. This is the simplest, smallest sugar with just 3 carbons. But a lot of other sugars have 4, 5, and 6 carbons. Now, we're not going to go through all the different possible ones. If you go on and take some biochemistry, or you may see it in your professional schools, then you'll learn all of them. We're going to skip right to the most common ones, like glucose. So glucose is the most common sugar, the most important sugar probably in life. It's the one that everything bigger gets broken down into, gets converted to, and then glucose gets stored as glycogen in the body. And glucose itself can be converted to ATP and do some other stuff. Glucose is a 6-carbon sugar called a hexose, because ose means sugar and there's 6 carbons. And we're going to look at its Fischer projection. And we're not even really going to worry about its dash and wedge notation. Because it's big, it ends up being really confusing. So just like glyceraldehyde, glucose is going to have an aldehyde on the top and an alcohol on the bottom, CH2OH. And instead of one line in the middle with stereochemical significance of OH and H being on one side or the other, it has 4 because it has 6 carbons total. So the order for glucose goes HOH, like this. And because we drew that bottom one to the right, this tells us that what we just drew is D-glucose. So this is the D enantiomer of glucose. If we want the L-glucose, we don't just flip that one, we flip all of them, because the D and L have to be complete mirror images. This is one thing that makes the Fischer projection really nice. Instead of dealing with dashes and wedges, we just flip the sides. So everything gets flipped. And this is L-glucose. Well, I mean, in reality, you can't just take a molecule of glucose and turn it into L. I mean, you can actually, but that shows that's how you always find the enantiomer. Just like with the smaller molecules, if you flip everything completely, you make the mirror image, and that gives you the other enantiomer. L-glucose isn't so important. We're not really going to do much with it because it's not something that exists. It's not something that's important. I mean, it exists. It's not something that's important to our bodies. So we're going to mostly deal with D-glucose. What happens if you don't switch all the OHs? If you just switch some of them, or one of them, or whatever, you actually get different sugars. So rather than draw all these, I'm just going to pull up a picture because we don't need to know all of them. But I'm searching for all the aldohexoses. So that is sugars that have 6 carbons and an aldehyde on top. And like I said, you don't need to know all of these, but I want to show you what they look like. So all of these structures with different names, some which you may have heard before, mannose or galactose or some of these other ones, these are all different types of sugars that exist. Simple sugars, they're called, or monosaccharides. They all have 6 carbons. They all have an aldehyde on top. And the only thing that differs is the stereochemistry of their OH groups, of their alcohols. So you see glucose, the second from the right on the top there. And then you can look at all the other ones there. Notice these are all the D sugars. So the bottom carbon that, well, I guess it's technically the second from the bottom. All the OH is always pointing to the right. And depending on where the other ones are, that gives us our stereochemistry, or I'm sorry, our identity, our name. So the different sugars only differ by that, but they're totally different to your body. They're going to have different tastes. They're going to affect things in different ways. They're going to be processed by your enzymes in different ways, affect your blood sugar in different ways. Some of them may be more digestible than others, just because of that difference in the 3-dimensional orientation. Sound okay with that? Maybe? Okay. So then the next step is that to tell you that sugars don't actually really hang around like this much. This is more like an intermediate structure. If you actually isolate sugars, they don't have this straight chain structure. They actually have a ring structure. So our next step is to learn how to draw these in their ring form, which is called the pyranose form. So let's draw glucose again. This time I'm going to draw the aldehyde all the way out. And I'm going to put this carbonyl oxygen in red. And you'll see why in a little bit. So here's the rest of glucose. So we take D-glucose, and rather than be in that configuration, what happens is this second from the bottom oxygen gets rid of its hydrogen, and connects up to this carbon. Now we know that carbon can only have 4 bonds. So in order for that carbon to have 4 bonds, it loses one of its connections to oxygen. And so that red oxygen becomes an OH. So that extra hydrogen kind of goes through solution and ends up over there. And then we can draw the result of that. So to draw the result of that, we use another kind of a structural projection called a Haworth projection for this, what's called a pyranose form. And here's how we're going to do that. It ends up being a 6-membered ring, so like a hexagon. That oxygen that was down there that lost its hydrogen, it actually ends up part of the ring. So the ring kind of goes around like this. And the ordering of the carbons is a little tricky to see, so we're going to use numbers to make sure we know what we've got here. So this is going to be 1, 2, 3, 4, 5, and 6. There's our 6 carbons. All right. So the one directly connected to the O in the ring, going around counterclockwise, or I'm sorry, clockwise, is 1, and then 2, and then 3, and then 4 and 5. And you'll notice there's no 6. Well, that's because if you look at what's going on here, these are the atoms that make up that ring. So this carbon number 6 is actually outside of that. It's not connected as part of that loop. But what we do know is that it's connected to carbon number 6. So to do the connections here, it ends up being important, just like with stereochemistry going back and forth on the straight structures. On a ring, that stereochemistry ends up being up and down. So whether an atom is on the top above the ring or on the bottom below the ring changes its 3-dimensional orientation and whether or not they're the same. So to show that, we're going to draw lines at each carbon that go up and down. And instead of and then we're going to put the OH and the H on each one depending on where it comes from. So I'll show you how to do that.
Wait, why didn't the hydrogen in this?
Because oxygen likes to have 2 bonds and carbon likes to have 4. So the hydrogen kind of ends up switching from that oxygen to the carbon so that nothing has too many bonds or too few bonds.
But then isn't it not a D-glucose anymore?
It is actually. This is going to be another form of D-glucose. It didn't lose it. It just kind of transferred it to another part of the molecule. Yeah. So the formula ends up being the same. And we can check this too. All right, so to finish setting this up, we're going to take that 6th carbon and put it up here on the back left. That's number 6. And then for the other ones, and then there's also an H here. For carbons 2, 3, and 4, if the Fischer projection shows the hydrogen going to the left, we're going to put it up on the ring structure. And if it shows it going right, we're going to put it down on the ring structure. So number 4 gets the OH which way, left or up or down? Down. Everybody see that? It's on the right on carbon number 4. So we're going to put it down over here, and that means the H goes on the top. Carbon number 3 is going to be up. Carbon number 2 is going to be down. And then carbon number 1 could kind of go either way. because in the original structure, that's the O, that's the red O, the aldehyde O. And that doesn't have a specific orientation. It can flip around. And so that can go either way. So let's just draw it up for now. And let's make a note that this could be up or down. Yeah. Yeah, and so essentially this H went from here to here. Because this O used to not have an H attached, and now it does. Yep, that's this part right here. That's carbon number 6, which is connected to carbon number 5. So the only new connections, yeah, go ahead. Which O? This one? That's here. That's actually inside the ring. So that's still connected to 5, but now it's also connected to 1. So it made a connection from there all the way up to there and kind of curled back on itself. Okay. So let me show you the picture in the book. They kind of do a good job of showing how it actually curls around on itself. So it may be, oh, I have to go back to load it up again here. Sorry. That again. All right, so take a look at what they show here. So this is what we just did. We've got this open chain form. Yeah.
So the H that falls off at carbon number 5, is that the one that gets attached to the content?
I mean, technically it's not the exact same one because it would just come off into the solvent and then gains one from somewhere else. Yeah. I guess it could be the same one, but that's why we don't draw it specifically like going from here to here because it's not the exact same one. It's kind of like it falls off and then goes back on later.
All right, I don't really understand it. So left equals up, right equals down. Like, what is that?
So here's an example. Here's what's going on. We're taking this structure and we're connecting it. So we're kind of like turning it on its side. So anything that was on the right is going to end up being down when it gets turned. Okay. If you want to actually do it, we don't have time right now for everybody to do it, but at some point you can get the models out and you can build that thing and you can see that anything that was on the left, when you like turn it around and make the ring, is going to end up going up, and anything that was on the right is going to end up going down. So that's where that comes from. It's because we're looking at it in a different orientation. It's kind of like it's laying down when it forms the ring. Yeah.
So on carbon 5, the hydrogen's on the left. So on the other one, why is it going down instead of up if the left goes up and not down? Does that make sense?
On carbon 5, the oxygen is on the right.
No, the hydrogen is on the left.
The hydrogen is on the left.
Oxygen goes up, but on the other one, it's going carbon 5.
Oh, over here? Yes, okay, I see what you mean. So on number 5, the hydrogen is on the left, but it ends up going down instead of up. Yeah, that's because this one's going to turn a little bit different way because its oxygen has to connect. So that's why we said here this only works for the 2, 3, and 4, the other ones. Because the 5 is the one that has this. So for D sugars, which is all we're going to deal with, the CH2OH always goes up, always goes on that exact same position on the back left. That's always where that CH2OH is going to go. So the only space left for that H then is the bottom. This is how it twists around. Yeah. It's not there anymore. We took away the double bond because carbon can only have 4 bonds. So if something else is going to connect to it, then those electrons can't be there anymore. And so those electrons actually end up making the connection to the H over here instead. So that's where the double bond used to be, this line right here. And so now it's a single bond, and that O is connected to an H instead. I know it's tricky. I know it's hard to see. If you can do it with models sometime, give it a try. It may help you see that. There's also some different pictures and some practice in the book on how to do that. So this could be up or down thing. There's actually different names for whether it's up or down. We're not going to worry about that. If you look in the book, you'll see those names, but you don't have to know them. It's alpha or beta. So with our last 10 minutes or so, I want to show you what happens when these things start linking together. So these are all the monosaccharides, the simple sugars. Simple, right? Simple? No, I know it's not simple. But what we get in nature is these sugars can get hooked together and form disaccharides, which are 2 sugars hooked together, or they can form polysaccharides, which are many sugars hooked together. And there's a few different forms of those. So I'm not going to try to draw those. I don't think you should try to draw them, although you're welcome to if you want. But we're going to look at some of the pictures from the book of how these things come together.
So do you like understand like this? Like, do you actually understand it?
Define understand it.
Like, you know what's going on?
Yes, yeah. Yeah, I know what's going on.
It's so
That's funny. Do you not know what's going on? Well, we'll work on it. You'll get it. So another sugar we're not going to mess with because I don't want to confuse you further, but you should at least know what it looks like, is fructose. It's a really common sugar produced by fruits. And instead of being an aldose, a sugar with an aldehyde, it's a ketose, a sugar with a ketone. The carbonyl in fructose is on the second carbon instead of the first. So instead of being an aldehyde, it's a ketone because it has carbons on either side. So that's going to change its properties a bit. And one of the ways it changes it is instead of, when it circles up, instead of making a 6-membered ring, it makes a 5-membered ring. So when you see that 5-membered ring, often what that's going to be is fructose instead of glucose or some of the other aldohexoses. Mm-hmm. Yep. Yep, so you can see all the numbers here. So 5, there's the OH, and that O is going to get connected to 2. So the 5, there's the O, and then it gets connected to 2. And this highlighted part is what used to be the double bond. So
wherever there's a double bond, that's where it's going to go.
That's where it's going to go. Yep. Yep, for these, yep. All right, so you can look through the book. There's some other types of things that they talk about too, but let's skip over and start looking at some of the disaccharides. So there's a couple things that separate disaccharides from each other. One is which sugars are used to make them, and the other is how are they linked. So in this example, maltose, which is a sugar that's made from that's in like germinating grains, like when we talk about malt, that's where that comes from. What's happening is you have 2 glucose molecules that are just a little bit different, the alpha and the beta. You'll notice that the OH here is down and the one over here is up. And they get linked together between 1 and 4, losing water. So the H2O goes away, and these end up connecting like that. And that's called a glycosidic linkage or a glycoside bond. When those particular 2 sugars connect in that particular way, we have maltose, which is a different sugar. A disaccharide has different properties, different tastes, metabolized differently, all of that. So that's how a disaccharide works. If we change that up a little bit, so if instead we take, let's see where you can see this there. If instead we take a molecule of galactose and a molecule of glucose and hook them up between carbons 1 and 4, we get lactose, which is milk sugar, the sugar that's in milk. It's still a 1 to 4 linkage. It's still that glycosidic linkage. But again, a totally different sugar. Lots of people who could eat maltose all day would not want to eat lactose all day because it would cause problems, right? You're lactose intolerant. You don't have enzymes that can break that particular type of linkage down, even though the other sugars are so similar. That's why this stereochemistry, these little differences, make such a big difference. And then probably our most common disaccharide is when you take a glucose molecule and link it up 1 to 2 with a fructose molecule. When those 2 hook together in a glycosidic linkage, you have sucrose, which is our regular table sugar, white sugar that gets refined from sugar cane or sugar beets. It's the same sugar that's in brown sugar and raw sugar and all those other kinds of sugar too. They're just different amounts of refinement. But that's our standard table sugar. It's 50-50 glucose and fructose. All right, so now let's look at some big ones. We're going to look at two big types of large polymers of glucose, which is glucose molecules hooked together over and over and over again, thousands and thousands of them. There's starches and there's cellulose, different parts of plant structure. They're all made of glucose, but only the linkages are different. And the different linkages end up having huge consequences for how we interact with them. So this one, for instance, is amylose. It's a bunch of glucose molecules hooked together 1 to 4, and it makes a pretty straight chain that ends up kind of curling on itself and hydrogen bonding. And this is one of the major starches in like cornstarch or potato starch or rice. Actually, well, depends on the types of those things. But then there's another, and then we have an enzyme called amylase that cuts that apart. But then compare that to this one. This is amylopectin. Amylopectin has that same 1 to 4 linkage of those glucose molecules over and over again. But then it also has some 1 to 6 linkages, which makes it kind of branch out more like that. And that branching makes it have really different properties. So for instance, if you look at rice, longer grained rice has more amylose and less amylopectin, and shorter grained rice has more amylopectin. And so it gets stickier. If you ever notice that sometimes rice is like separate grains and sometimes rice is like really clumpy together. There's even another kind of rice called glutinous rice. It doesn't have any gluten in it, but it's almost entirely amylopectin, and it makes those like totally mushy kind of structures that almost doesn't have any separate grains at all. And that's because of the way that these different sugars are linked together. When you have that more branching, you have more of that stickiness, more of that that starchy feeling to it. And then comparing those to this other one, which this isn't a great picture, so we're going to look at another one too. Cellulose is totally different. Cellulose is like wood, right? Like the stem parts of plants, the parts you can't digest. It's what we call fiber, because you can't digest it, and so you eat it, it just kind of pushes everything else through. It's still just made of glucose, just like amylose and amylopectin, our standard starches. But the linkage is different. We have this 1,4 beta linkage, which lines everything up in such a way that cellulose ends up being much, much harder to break apart. So do you know who can get nutrition from cellulose?
Plants.
No, plants make the cellulose. Close though. I'll give you a hint. It's not plants. What kind of animals?
Deer.
Cows.
I don't know about deer, but cows, yeah. Probably deer
birds.
also. Yeah. Anything that has, no, I don't think deer can. Yeah, they probably can.
Fox.
Not foxes. Anything that eats a lot of grass or leaves or
Cows.
those kinds of things. So cows, sheep, probably not dogs. I don't think pigs either. You need those multiple stomachs where you keep grinding the stuff back down, re-swallowing it, redigesting it, grinding it up again, swallowing it back down, having all this different enzymatic action. Because even though this is how the book shows the structure of cellulose, it's really more like, find a better image of it. There, yeah, it's really more like this. So let's take a look at this so we can show what's going on here. So this is really what cellulose looks like. These here are the individual chains that we just saw from the picture in the book. That's an individual chain, and then this one's another individual chain, and they're connected through these hydrogen bonding interactions. So lots of hydrogen bonds here. Remember hydrogen bonds? Everybody's favorite, intermolecular forces that hold things together so tightly. But when you have that many hydrogen bonds holding everything together, you end up with an extremely strong structure. And so that's why our enzyme, that's one of the reasons our enzymes have so much trouble with cellulose and why we don't get nutrition from it, why we digest it. Have you ever heard that like some vegetables, you get negative calories from them? I don't know if you've ever heard of that, like celery and stuff. It's because they're pretty much just cellulose and water. So you get zero energy from it, and you actually use up energy by trying to grind it up and chew it and digest it and push it through your system. And so that ends up making negative calories. What? I don't know. I think celery is one of them. Maybe kale, stuff like that. Like super.
Good for you.
Yeah, that's why. Well, that's why they say they're good for you, because they take, you use energy to eat them instead of getting energy when you eat them. Yeah, that's kind of how it goes. But yeah, so that's cellulose. So that's another polysaccharide. So, right. So if you're going through the book, skill-wise in this chapter, and we can practice a little more on Tuesday, but skill-wise, you should be able to talk about these three-dimensional structures and determine if things are enantiomers, if they're superimposable or not, based on rotating them around and making them match up. For the quiz next week and for the exam, you can use the models if you need to use the models. But probably for the final exam, we won't use the models. But you should be able to draw these things in 3 dimensions and understand the dash wedge notation, the Fischer projections, and the ring, the Paretos projections. You should know what they are. You don't need to be able to interconvert between the Fischer projections and the other ones. But if I showed you a structure of like, you know, if I showed you a D structure, you should be able to give me the L structure. You should be able to know that this means that these are actually different. You don't need to memorize the structures. The ring? Yeah, you should be able to do that. So if I give you a Fischer projection, you should be able to put it down into there using the left up and right down rules. Any of those six ones. But remember, it's always going to be the same except for the position of the OHs. But it always makes the same thing.
Yeah, I know. I'm just saying, like, some of these things.
Yeah, so
Memorize this one and
no, I would say you want to be able to actually do it. So you want to be able to.
How do we know for like carbon number 1?
You don't for carbon number 1. So carbon number 1 can go anywhere you want. Right. So for instance, and in the book here in section, what section? You guys can go if you need to, but in section 16.4, there are practice problems where they go through this example, they show you how to do it, and then they give you some different, they say, okay, try it with galactose, try it with ribose, and see what you get.
And that's the first one.
The Haworth projections, yeah.
Haworth.
And then there's some practice there also. All right, thanks everybody. See you next week.